Hope everybody had a good weekend. Yay. Hope everybody had a good weekend. I do have your exams to hand back. I'll do that at the end of the period. Grades are also up on Carmen, so hopefully when you get your exam back, please double check that to make sure that the posted grade is correct. And actually also just a note that if you guys hopefully double checking that your homework grades are posted on Carmen as well. Homework 3 I think should be up. I'll hand those back on Wednesday. But if you have a grade, if there's no grade posted where you know you turned a homework assignment in, please let me know. Our grader is not error-free, I'm sure, with posting grades, so just let me know if there's anything there that is not there that should be there. Yes, sir.
Do you know the statistics for the exam?
Yes, I think you can see those on the... You can't see those? Okay, I'll try to unveil those. The average was a B+, I believe, so that's pretty good. There were a few scores above 100%, but most were in the B to low A range, I would say. But yeah, I thought I had that enabled, so I'll try to make sure that's visible to you guys. So in general, very good job on the exam as a class overall. And I guess if you were not happy with your score or anything, please come talk to me. I'd be happy to discuss my grading of it or kind of where you're at in the course. I would be very happy to talk to you. The sooner the better as far as all that stuff goes if you're concerned about your grade. There is a fourth homework assignment posted. I think it's due on, I think I made the due date on the 24th, so next Monday. Check that out. I will get solutions to the suggested exercises up later today. And I will also post solutions to the exam later today. That's one other thing I wanted to do. Are there any other questions, comments before we get started today? Okay. So we're going to resume Chapter 5. And we'll pick up new material in the middle of page 6 there on your Chapter 5 notes to remember where we're at. But quickly, a brief review of what we're talking about here in Chapter 5. And that is jointly distributed random variables. So again, the first chapters 3 and 4 of this class, we looked at just one random variable. And now we're talking about two random variables. So when we can look at sort of a joint behavior of more than one random variable. And so now we're going to have pairs of random variables, x, and y. And our generic notation there. And then just to remind you, if x and y are both discrete random variables, then we're going to be talking about a joint probability mass function. So sort of like the just the regular probability mass function we saw back in Chapter 3. We have a joint version of that, which simply gives us the probability that our random variables each equal some number. And again, for a valid probability mass function, we just need to make sure that all the probabilities are bigger than or equal to 0, and they all add up to 1. Same sort of a very natural extension of what we saw before. And if x and y happen to be continuous random variables, then we'll have a joint PDF, probability density function. And that's any function such that we can define probability by integrating over sets of numbers. So the extensions are exactly what you would expect them to be from chapters 3 and 4, talking about sort of the exact same type of things, just looking at two random variables now instead of one. So on Friday we talked about things like independent random variables. We introduced conditional distributions. I guess the first thing we talked about was marginal distributions, and kind of going to continue using those ideas here in today's lecture. So picking up with an example of a conditional probability density function for continuous random variables. Here we are at the middle of page 6 on your Chapter 5 notes. So now the two random variables we're going to look at are the tire pressure in the front wheel of this vehicle. So x represents the air pressure in the right tire, and y represents the air pressure in the left tire. And we're going to say that they have this joint probability density function. So when x and y are between 20 and 30 each, then they have some functional form there, and it's 0 outside, 0 otherwise. So kind of following up from brief discussion on Friday, I did want to maybe show you a picture of this probability density function, which is not in your notes, just to kind of give you an idea that it's now with two inputs. Then we now have a three-dimensional plot, and so here might be my x random variable, and here's my y. So both of those go from 20 to 30. And then now the probability density function is going to be a three-dimensional surface there instead of just a curve or some sort of a graph like we've looked at before. And you can imagine there's little dotted lines coming down here, and then outside of this thing it's going to be equal to 0. So that it's only positive sort of in the range that it's defined there. So if you're a visual person like me, maybe that's helpful to you. But in any case, we can use this joint probability density function to figure out a conditional probability density function for y given that x is equal to some value lowercase x here. So if you remember the conditional PDF, we're going to use subscript of y given x, and this is the density of y given some small x value. And if you remember from Friday, the definition of this thing is equal to the joint density divided by the marginal density of whatever you're conditioning on. So we're conditioning on a particular value of x, so we want to divide by the marginal density of x. So that's what we need to find here in this example. So we already have the joint probability density function. We already have the numerator. We just need to figure out what the denominator, the marginal of x, is. So we need the marginal distribution of x. And to do that, again, we can integrate over our joint density, integrate over all possible y values. So kind of get rid of all the y's that we have floating around there in our joint probability density function. So the marginal density for x, marginal probability density function of x, is we're going to take the integral over all possible y values of the joint density. So we're integrating with respect to y here. So far that's just by definition. And then for this specific example, that the joint PDF is only positive for y when y is between 20 and 30. So we can write down our specific endpoints here, and then the joint density is 3 over 380,000 times x squared plus y squared. Okay, and so now it's kind of, again, a simple matter of figuring out the integral here. Remember, when we're integrating with respect to y, you can just treat x as a constant, keep that fixed. So this is 3 over 380,000 times x squared y plus y cubed over 3. Then we'll evaluate that at our endpoints, 20 and 30. And so this is 3 over 380,000. Yep. So if I plug in 30 first, I have 30x squared plus 30 cubed over 3. And subtract off evaluated at y equals 20, so that's 20x squared minus 20 cubed over 3. So 2. And if you simplify that out, that should be 3 over 380,000 times 10x squared plus 19,000 over 3. Okay, and this is for when x is between 20 and 30. Okay, so nothing too crazy there, just finding the marginal distribution of x, the marginal PDF. And let's Well, I've run out of space. I never do a very good job of this. Let's finish this problem out over here to the side. So then our conditional density of y given x, again, is just equal to the joint density divided by the marginal of x. So now we can just plug some things in there, and I'll let you check that this is x squared plus y squared divided by 10x squared plus 19,000 over 3. And again, this is for y between 20 and 30. Okay, so kind of thinking about what we found here, this says that for a particular value in the air pressure in the front right tire, for example, so suppose the air pressure in the front tire is 25. I plug in 25 for x here, and then I'll have sort of a conditional density for the air pressure in the left tire, given that the right tire is at 25 psi. So it's given that we know something about x, this is kind of what the behavior of y will look like for that particular x value. That's kind of the idea of the conditional PDF. We're conditioning on a particular value of one of the random variables. Everybody okay with the calculations there? Yes, sir.
Can you include like x as well for that one or not?
Oh, for the bounds. Well, yeah. So the question was, should you include the bounds for x? I guess maybe technically yes, but we're assuming that we've observed a particular value of x, right? So that kind of goes back to the fact that we're assuming we've observed a particular value of x, which we've said can only be between 20 and 30. So we're sort of, I'm not writing that down, but sort of implicitly assumed there. Great question, though, yeah. But the idea is that kind of looking at this formula right here, the x is some number. It's whatever you've observed it to be, you can kind of sort of consider that as a fixed thing in there. And then there's the y variable could be anywhere between 20 and 30. Very good question. Okay. So next question here, are x and y independent random variables? So if we remember how we want to check, how we can check independence, there's a few ways we can do this. So sort of the first way that we can do this is to see if the joint density is equal to the product of the marginal densities, right? So if the joint density is equal to the product of the marginal density of f times the marginal density of y, then they are independent, right? It's kind of the same idea as before. It's like probability of A and B equal to the probability of A times B, times the probability of B. But then sort of an equivalent way would be looking at the definition of the conditional PDF, right? So if my if I can write that joint density f of x, y as this product here, then the conditional distribution of y given x should be equal to the marginal distribution of y. So think about it, if this numerator can be written as this product over here, then the marginal distributions of x will cancel out, and we'll have sort of simplification here. So we can either check that, or we can see if the conditional density of y given x is equal to the marginal density of y. So we want to check either one of these. If either of those things are true, and they're both equivalent, so you can check either one. If either of those are true, then we have independence. Okay, so similar calculation as we did to find the marginal distribution of x, we could do the same thing for y. So again, if we look back to this calculation, if we just took the integral with respect to x instead of y, we'd get the exact same result. So sort of by symmetry from part A, the marginal density of y is going to be equal to the same thing we got as for x, so 3 over 380,000 times 10y squared plus 19,000 over 3. So I'll let you do that integral calculation again if you like. That's what we'll get for our marginal density for y. And of course, these two things are not equal, so the marginal density of y is not equal to the conditional density of y given x. So therefore they are not independent. So because the marginal density of y is not equal to the conditional density of y given x, then they are not independent. So kind of the intuition there is if I know something about x, that's changing what I will know about y. So the marginal density of y is something that I know nothing about x, and it turns out that distribution is different than the distribution of y if I know what a particular value of know something about the random variable x. So because the marginal is not equal to the conditional, then we have some sort of a relationship going on there. And again, so we use the second one. You could have just as easily shown that the product of the marginals is not equal to the joint density. That would have worked just as well. Is that okay with everybody what we're doing here? Okay. Okay, so that's concludes our discussion on section 5.1. Moving on to section 5.2, again, kind of progressing through the same, stepping through the same types of things that we looked at back in chapters 3 and 4. So here we can talk about some expected values for joint random variables, and we can also talk about a few other things here in a second. So the corollary of expected values from chapters 3 and 4 is right here. So if I have x and y are random variables with a joint PMF or joint PDF, depending on if they're discrete or continuous. And I have a particular function h of x and y, so I can have a function of both of those variables now. I can find the expected value of that function in the same way that I would have before. So taking a sum over the function times the PDF, the probability mass function, or doing an integral over that function times the PDF. So same kind of an idea as we've seen before, just double summations or double integrals instead of just single summations and single integrals. And again, just note that there is no multivariate calculus requirement for this class, so I won't be asking you to do any double integrals that are like this. I might be asking you to do some things like we did in the example before, where it's maybe a function of two variables, but you're just doing a single integral, but won't be anything more complicated than that. Okay, so let's look at an example of this, how we can apply this concept. So say the instructor in a certain class has given a short quiz consisting of 2 parts, and for any particular student, let's let x equal the number of points they earned on the first part, and y equal the number of points they earned on the second part. And then we have so we're going to suppose these are discrete random variables. We're going to suppose they can only earn 0, 5, 10, or 15 points on the second part, and only 0, 5, or 10 points on the first part. So we have this joint probability mass function, joint PMF here, given in the table. And those kind of like what we've looked at before. So first question here is suppose that the score that the instructor writes down is the sum of the scores on the first and second parts. What is the expected score that we're going to get? So what's the expected value of x plus y? So what we can do here, Again, now this my function of x and y is just the sum of x plus y. So if I want the expected value of that, expected value of x plus y, I can just take the sum over all the x values that I have and the sum over all the y values that I have, and let's take x plus y times the probability mass function of those values. So x can equal 0, 5, 10, y can equal 0, 5, 10, or 15, so we have a number of terms to add up here. This is going to be if x and y are both 0, so 0 plus 0, the probability of them both being a 0 here is 0.02, so I can weight it by that, so 0.02. Next, if x is 0 but y is 5, I have 0 plus 5. The probability of that happening is 0.6. And so on. I'm going to get lazy here and use some dots. All the way up to if, well, let me come down here. All the way up to if x is 10 and y is 10, that has probability 0.14. And then finally, if x is 10 and y is 15, I have 10 plus 15. Probability of that result is 0.01. So for each x and y combination, I'm just taking the sum of the individual values, then weighting it by the probability of each of those things. And if you work this out, it'll be 14.10. So the expected score on this whole thing is about 14. Everybody okay with that? Okay, just a little bit more complicated. What if instead of the sum of those two parts, I just record, the instructor just records the maximum of the two scores? So what's my expected score if I'm looking at the maximum? So this is not as obvious, but again, now the function that I want to take the expected value of is just the max of x and y. So the expected maximum score here, the expected max of x and y, I'm going to do the same thing. Just sum over all combinations of these things, and the functional value I use is just the maximum of those two things. So again, sum over all x, sum over all y. I'll take the max of x and y times the probability of that result happening. So same exact setup, I'm just, my function of these two things is now different. So what we have here, this is if x and y are both 0, we have the max of 0 and 0 times probability, 0.02, plus the maximum of if x is 0 and y is 5, the probability of that is 0.06. Let's use some more dots. All the way up to the max. If x is 10 and y is 15, that has probability 0.01. So kind of just writing out very formally what we have here, and then again you can just pick out the max of those two numbers. So this will be equal to 0 times 0.02 plus 5 times 0.06, and so on, all the way up till we get to the last one, which is the max of 10 and 15 is 15 times 0.01, and if you work all that out, you should get 9.60. So skipping over a lot of those steps, but the idea is we're just taking of the possible combinations we have, we're just taking the larger of the value and using that for our expected value. Questions, comments? Is that all right? Okay, so this brings us then to the next idea. But before I resume on page 8 of our notes here, I wanted to kind of revisit an example we have and sort of try to motivate where we're going here next in this chapter. So if you remember at the beginning of lecture on Friday, we took an example here. So we're looking at weight and height. And what we're going to be thinking about here next is, so we've talked a lot about variables being independent. So we looked at x and y being independent or not independent, but we haven't really talked about. So suppose they're not independent, then sort of how strong is that relationship? So we want to have some way of sort of quantifying a dependence relationship. So if they're not independent, how dependent are they? Is kind of where we're going to go here. So remember we looked at if we had height and weight and they both had normal distributions. We looked at the weight had a certain normal distribution. The height had a particular normal distribution. I'll refer you back to the slides in the beginning of the previous lecture. So let's suppose for a minute that they are independent for a minute. So if the weight and height of people are really independent, which probably not the case, then remember we used a scatter plot here to sort of represent sort of their joint behavior here. So the histograms here for the weight and the height show sort of the marginal behavior, and then these scatter plots over here we can look at sort of their joint behavior. And yes, again I have switched my axes here. So can anybody tell me why this picture sort of shows that they're independent? If we pretend for a minute that they are independent, anybody have any intuition, Andrew?
So there was like a mean or like a group where like they would all be, if they're independent, they're also scattering outside of it.
Yeah. So there's sort of there's just sort of a scattering here. They're kind of all just in a single cluster. There's not really any type of a pattern going on here, right? This is kind of a circular shape. It's kind of in this nice oval shape here. So maybe to convince you why this is independence and not otherwise, let's maybe look at the case. Of course, height and weight really are related, right? Taller people are probably more likely to weigh more. Shorter people probably weigh less a little bit. So we probably have something more like this scatter plot going on if we're looking at thinking more realistically. And again, I made all these plots at the same time, and they made the mistake for every one of them. So the axes should be labeled. The label should be switched there. So which one of these, looking at this sort of visually, which one of these would you say has a stronger relationship? If you were picking between these two. The one on the right. Yes, exactly. Why did you say that? Yes. So it's. Say that again. Yes, right. So they're a little more closely grouped together, right? They're kind of more tightly clustered here, whereas these are sort of a little bit more spread out. But the point is that there's sort of that diagonal relationship going on here, right? So over here, if I know that your weight is at the larger end of this spectrum, that sort of corresponds to sort of a larger height. So if I know that your height is taller, it's more likely that your weight is going to be larger. It's kind of what these pictures are saying anyway. So compare that maybe back to here, where if I know something about your height being out here, I don't really know anything about what your height's going to be. So if I sort of look at just this part, I still sort of have the full range of height values in there. Whereas in these plots over here, I have some sort of a stronger dependence going on here, where if I know something about your weight, that tells me something about your height. So yeah, I don't know if these pictures are helpful, but it's kind of thinking about. So here we can see that there is some relationship, but there's also a different strength of a relationship here, right? On the left side, it's not quite as strong. On the right side, it's maybe a little stronger. If we want to talk about just wanted to put another picture up here of maybe this is what the joint density of weight and height might look like. So here on the left side, it's sort of a heat map, but on the right side, there's bit more of a three-dimensional picture of what that joint density function might look like. So we'll talk more about these kinds of things later, but just to kind of show you a picture of what these density functions might look like jointly. So anyway, that's just kind of illustrate how can we quantify the relationship between two things that are not independent. How can we sort of quantify their dependence? And that's what that leads us into this next idea. This leads us to this idea of covariance. So by definition, the covariance between two random variables x and y, we're going to write that COV is for the covariance, and that's simply equal to an expected value. So we're going to take the expected value of x, subtract off its mean. So this is the expected value of x. And we're going to take this times y minus its expected value and take the expectation of that whole thing. So again, if we have discrete random variables, remember that involves taking a sum. Now our h of x, y function, this is now x minus the mean of x times y minus the mean of y. So if that's our function, I'm just sort of plugging this into that formula that we put up earlier. So I'm going to sum over all x and y values and then fill in the functional values of those things times its probability. For the covariance, I'm going to do the same thing but just with integrals. So this is our formal definition of what covariance is, and again, this is going to allow us to quantify how dependent two random variables are. So just two more notes is that if I look at that definition a little more closely, if I take the covariance of x with itself, that just gives me the variance. So remember, the variance was the expected value of x minus its mean squared, so you can write that out, x minus mu of x times x minus mu of x. So that's just plugging in x twice there in our covariance formula. And then a shortcut for actually how to calculate a covariance. This is a slight simplification here. So sort of like we had a shortcut for calculating the variance of expected value of x squared minus the quantity squared of expected value of x. You can sort of do a similar thing here. That'll usually make your life a little bit easier. Okay, so before we do an example, I wanted to introduce one more thing here, very closely related to the covariance. So have you guys heard of covariance before? Is that a new idea? That's something you've heard before? Okay, well, regardless of that, I'm sure that everyone has heard of correlation, right? That's gets thrown around in news articles all the time. So very closely related. So the correlation of x and y, which we're going to denote with either CORR, the correlation, or the Greek letter rho, is going to be defined as follows. So it's defined in terms of the covariance, but you can kind of think of this as sort of a standardized covariance. So I'm taking the covariance and I'm dividing by, I should say what I'm dividing by here. These are the standard deviations. So I'm taking the covariance and I'm going to divide it by the standard deviation of x times the standard deviation of y. So I'm sort of standardizing how strongly they are related to each other. And what this tells us here is this tells us the strength and direction of a linear relationship between these random variables. So this is something we'll see and we'll use later in this course to a greater detail. But that's kind of the intuition, is that the correlation tells us how strong and what direction. So is the relationship positive or negative? Specifically, we're looking at a linear relationship here. So throw a few pictures at you to kind of illustrate that we're talking about a strength and direction. Again, this is not in your notes, but kind of here we have a spectrum. Over here at the left side we have perfect positive correlation. So they kind of lie on a perfectly straight line, and it kind of goes from strong positive correlation all the way down to strong negative correlation. So again, when I'm talking about direction, here. I'm talking about positive or negative. And so you can see that here I have positive relationships, and moving over, I have negative relationships going on there. So it's kind of just a picture to show you sort of a spectrum here of correlations that we might get. Okay, so a few properties of correlate. Yes, sir.
When we're dealing with two variables, for correlation, is it always going to be kind of linear, or we can either see
Something nonlinear. Yeah, exactly. Great question. So the question was, if you're dealing with two variables, of course you could have a nonlinear relationship, right? It could be something that's sort of maybe in like the shape of a parabola or something like that, right? So yes, so that's a great point, is that correlation only. So yes, you could have that relationship, but correlation will not measure that. So correlation only measures a linear relationship, so sort of a straight line relationship. So just because, again, this picture, these plots don't really show that, but just because the correlation is close to 0, for example, that doesn't mean there's no relationship. That just means there's no linear relationship between those two variables. So that's a great point. Maybe let's make a note of that. So 0 correlation means there's no linear relationship between x and y. That's a great point. That's something we'll see again also later in this course when we talk about regression. Whoa. Okay, so two facts about correlation before we do an example here as well. Is that if I have a linear combination of x and y, so if a and c are both positive or both negative, so long as they're not 0, the correlation of ax plus b and cy times d is the same as the correlation of x and y. So if I have linear transformations going on there of my variables, that's not going to change the correlation. And intuitively, that should make sense, right? So remember, the correlation measures the strength and direction of a linear relationship. So that correlation shouldn't be affected by the units that you use. So if I have my weight in pounds and height in inches, I would expect the correlation between weight in pounds and height in inches to be the same over here as the weight in kilograms and my height in feet. So that's kind of the intuition there, is that the units that you use don't affect what the correlation is, and that should make sense. Height and weight have the same relationship whether you're measuring them in inches and pounds or feet and kilograms. That's the point of this first point. And secondly, for any random variables, the correlation is always going to be between positive and negative 1. Sort of hinted at in those previous pictures that I put up there, it went from 1 all the way down to negative 1. The correlation will always be between positive and negative 1. Okay. 2 more items. Again, we're talking about how to quantify dependence, right? How to put a number on how strong a relationship between two variables is. And that's what the covariance and correlation is. So if x and y are independent, then you could think about they're unrelated. They have no relationship to each other. So remember, the correlation of x and y is equal to the covariance of x and y divided by the standard deviations. So if the covariance is 0, we're saying that there is no, if the correlation or the covariance, same thing, are equal to 0, then we're saying there's no relationship. So X and Y independent means that the correlation is going to be 0. But unfortunately, the opposite is not true. So if you have 0 correlation, that does not imply independence. You can sort of cook up an example that doesn't hold. But in general, the intuition there is good. So low covariance or low correlation means we have something that's close to being independent. And then the correlation can only be plus or minus 1, again, if we have that perfect linear relationship. So only if y is some linear function of x. That's the only way that we can have correlation equal to positive or negative 1. Okay, enough definitions here. Let's do an example here. If you remember going back to our earlier in this chapter, we were looking at the dinner price example where X was the price of one person's meal and Y was the price of the date's meal, maybe. And we had 3 choices and probabilities as such, and we found the marginal distributions. So this was something we did before as well. So if we want to think about calculating the covariance, we can do that as follows. So remember the covariance, our shortcut here, is the expected value of X times Y minus the expected value of X times the expected value of Y. So let's compute each one of those parts, and we'll be on our way. So let's start with the marginal ones. So the expected value of X. Again, this is just like what we did back in chapter 3. We'll take each possible value of X times its probability. So if X is 12, that happened with probability 0.2. X could be 15 with probability 0.5. And X was 20 with probability 0.3. And if you calculate that out, that's $15.90. Okay, we can do a similar thing for the expected value of Y. It was 12 with probability 0.1, 15 with probability 0.35, and 20 with probability 0.55. So you work all that out, that should be 1745. Okay, and then we just need to find the expected value of X times Y. And for that we'll use, kind of like we did before with the sum and the maximum example, we'll use their joint distribution, their joint probability mass function. So expected value of X times Y, we can just go through each combination there. So if X and Y are both 12, we have 12 times 12, and that happened with probability 0.05. If X was 12 but Y was 15, that also happened with probability 0.5, and so on, all the way up to if they're both $20, 20 times 20, and that happened with probability 0.1. And if you work all that out, that should be 276.70. So kind of glossing over maybe some of these steps, but again, if I want the expected value of a function of X and Y, I just, for each possible combination of X and Y, I calculate that function. So here it's X times Y, and then I weight that times the probability of that result happening. So hopefully I'm not skipping over too many details here. But anyway, now we're ready to calculate the covariance. So the covariance of X and Y, that's the expected value of X times Y, so 276.70, and then minus the product of their individual expected values, so 1590 times 1745, and that will give you negative 0.755. So it's perfectly okay to get a negative covariance. Okay, so our x and I think we already talked about this, but are x and y independent, judging by this? No, right? The covariance is not equal to 0, so that means they're not independent. It's close to 0, so maybe you can think about they're almost unrelated, but they are in fact related to each other somehow here. Yeah.
What would negative covariance tell you about variables?
What would a negative covariance tell you? So maybe I'll jump back to these pictures here. So remember, the correlation is just the covariance divided by something positive. So both of these things are positive. Standard deviations are always bigger than 0.
Yeah.
So that means you'll have one of these type of pictures. So it'll be sort of a negative, sort of a downward trending relationship there if the covariance is negative.
Okay.
Yeah, great question. So the sign of the covariance and the correlation are always going to be the same. So if the covariance is positive, the correlation is also positive, and vice versa. Yeah.
So would like negative 0.75 be a high negative correlation, or is this less than that, low negative?
Yeah. So that this maybe illustrates the usefulness of the correlation. The question was, so is negative 0.755 a large or a small correlation? Well, we would have to calculate the standard deviations and divide by that, and I have not done that. So I won't ask you to. I would never ask you to calculate the correlation by hand. That would be tedious and cruel. For larger data sets, we'll use technology to do that. So that's why, and I'm not putting it on a relative scale of correlation here, but that's why correlation is helpful, because it lets me see. So relatively, is this a large covariance or a small covariance? So I should make a note to include the correlation next time I use this example. Is everybody okay with the calculation, though, at least? Okay. Okay, so that wraps up section 5.2. Let's say a little bit about the next 2 sections, and then I'll let you guys get out of here. Actually, I think this might be a good place to stop. I think we'll call it quits, guys. I do have your exams up here, so feel free to come grab yours. They are in stacks. I have A through D, E through K, L through R, and S through Z. So come get it. I'll have your homeworks 3 for you on Wednesday. Have a good rest of the day, you guys.